For today's lesson, we are going to go ahead and continue our coverage of how do we prove mathematical statements. So we're going to specifically be focused on section 3.3 and 3.4 of our text. So 3.3, in that section, we are going to consider proofs that involve the existential and universal quantifier. Whereas 3.4, we'll look at proofs that have a and statement in the premise or in the consequent. And so that, in other words, a conjunction, as well as proofs involving biconditionals. The way that I will be going about this video will actually be by focusing on the universal quantifier in 3.3 first, as well as the biconditional for 3.4, and then we'll discuss the existential quantifier towards the end. But before we begin, I want to pose the following question. What is a natural number? So natural numbers, we have 0, 1, 2, 3, so on and so forth. Prior to the late 1800s, this was a question that mathematicians would not have considered in any details. Just the numbers we have been working on with, that's the definition. It's just 1, 2, 3. They are just that. There's no need to define them. But with the rise of set theory, mathematicians, as we have seen with Frege, his work on arithmetic, as well as Bertrand Russell and Alfred Whitehead, sought to give to be able to define what a number was based on their axioms. And so both Frege and Russell Whitehead had the same definition for what a natural number is. In their definition, a natural number n is the collection of all sets that have n elements. And from this definition, they then proceeded to show that 1 plus 1 is equal to 2. Well, specifically when I say they, I mean Alfred and Whitehead. And as I mentioned in our first video, that was a lot of work, resulting in over 360 pages just to be able to prove that 1 plus 1 is equal to 2 from the definition n is the collection of all sets with n elements. Now, the axioms upon which modern mathematics is built upon are not those of Russell and Whitehead, but rather Zermelo and Frankel. And so this is the Zermelo-Frankel set theory. And so I've posted this slide a couple of times throughout our course. And so these are the axioms upon which mathematics is built upon. But I want to focus now on the answer to how are the natural numbers defined in the Zermelo-Frankel axiom set theory. And so the number 0 is actually defined to be the empty set. And so that is our definition for 0, it's just the empty set. And from it, we define 1 to be the set containing the empty set. And so the idea here is that by defining 0 to be the empty set, we have the set with 0 elements. We define 1 to be the set containing the empty set that has 1 element. And we continue in this manner. We then define 2 to be the collection of 0 and 1. But then that is a set. By definition, 0 is the empty set, so we have the empty set. And we have the set containing the empty set. And so that is what 2 is. And we continue, 3. Now we're looking at the set 0, 1, 2. And that will be defined once we plug in the previous definitions as empty set, the set containing the empty set, and then the set that we define for 2, which is now the set containing the empty set, the set containing the empty set, and the set of the set containing the empty set. And so now we have this set here. And so in general, we can define, if we have a natural number n, where it's defined as we have up here, we have a recursive definition, because we can define n plus 1 as n union the set containing n. And so if we look at, say, 3, so in that case we have 2 plus 1, and we see that according to this definition, we take 2, so here's our set for 2, and we take the union of that with the set containing 2, which is this here. And that's exactly what we have upon taking the union. And so this is just an aside to give you a flavor of, in a further course in set theory, how the numbers are actually defined. And then from it, as in our course we're not going to be using these definitions, but using the definitions of natural numbers, we will later define the rational numbers as a set. In a course in real analysis, you can define then the real numbers as a set as well. So for our first statement we're going to prove, we're going to consider the following proposition. Let A and B be sets. If A is a subset of B, we want to show that the power set of A is a subset of the power set of B. Now, how do we go about this? So what are the givens and what is the goal? So when we look at it this way, we are given that A is a subset of B. And our goal is to show that the power set of A is a subset of the power set of B. But if we rewrite this in terms of its logical form, what we end up getting is the following. For all, and in the past we've used lowercase x's, and Velleman does this, where he does use a lowercase x in this notation for inside a power set. But the convention that you will see in your further math courses is that whenever we deal with a set, we capitalize. And so instead of using a lowercase x, I'm going to go ahead and use a capital U. And so we have for all U is in the power set of A implies that U is in the power set of B. And so just to recap, the only reason I am capitalizing U here is to emphasize that we are dealing with a set. We have an element of the power set, and so by definition, that is a subset of A. And so this is our givens, and this is the goal that we're looking for. But now, when it comes to the proof, what we are going to do is take some arbitrary U. So I'm going to rewrite this. So the way that we're going to go about proving this is that we're going to we have A as a subset of B, and we're going to just choose some arbitrary U in the power set of A. And so I'm just writing this as some U is in the power set. And so the idea here is U is arbitrary. And what we actually do want to prove is that U is in the power set of B. And so here's how all of this translates. We have our assumption, A is a subset of B. And now, since our goal is a for all statement, by choosing some arbitrary U in the power set, so now we are assuming that this premise is true in this conditional. If we show that then U is in the power set of B, then the statement will hold true and we are done. And because we chose U arbitrarily, we also show in the process that this works for every single U in the power set of A, and that will show the claim. And so this is our goal, is to prove, to assume this and show that U is in the power set of B. Now, by definition, U is in the power set of B is equivalent, by definition, to U is a subset of B. Similarly, U in the power set of A is equivalent to U is a subset of A. But we have that A is a subset of B, and so now we're going into the scratch work. And so what we have now is the following question. If A is a subset of B and U is a subset of A, is it the case that U is a subset of B? Because if it is, then we are done. Because that's exactly what we are aiming for. We want to show that U is a subset of B, since that tells us that U is in the power set of B, which establishes in turn the goal, and that concludes the proposition. And if we see we can easily see this with a Venn diagram, that if we have that our set B is over here, our set A is in here, and inside it we have our U, then U being inside A, which is inside B, tells us that U must also be in B. But we haven't proven this statement yet. And so we need to prove this along the way to prove the given proposition. And so we have two things that we could do. We could prove this question inside our proof of the proposition, perfectly valid, or we can isolate it and have it as a standalone result. We can have it as a lemma for the proposition. And I'm going to do the latter. I'm going to first prove that lemma and then prove the proposition with it. And this is something that is good to keep in mind as you work through questions. Sometimes to make a proof cleaner, we can extract one of the arguments that we are using within it as a separate statement and then refer to it in the proof. So for example, we can now write the following lemma. So I'm going to just label this lemma 1 for the first lemma that we're covering today. And so we can say, let A, B, and C be sets. And so I'm writing it now in generality. If A is a subset of B, and B is a subset of C, then A is a subset of C. Now, to prove this, the statement A is a subset of C, by definition, that is, for all x in A implies that x is in C. And so what we are going to do is choose x to be in A, and then show that that x has to be in C, and that will finish it off. And so we go ahead, I'm going to go ahead and write this down. So I'm now doing my formal proof. So we could start off by saying let x be arbitrary. And suppose that x is an A. Now by assumption, A is a subset of B, and thus x is in B. And so here I'm using the definition of what it means to be a subset. Since A is a subset of B, we have that every element of A is necessarily an element of B. Similarly, since B is a subset of C, we deduce that x is in C, which shows that A, it's a subset of C, and we are done. And so here we have done a element chase proof. We chose our x to be arbitrary. Now, some commentary on Velleman's proof writing style. So he writes, and I wrote it, and I'm following his writing in this proof, where he says, let x be arbitrary, and suppose x is an A afterwards. If you omit let x be arbitrary, that is perfectly fine. Because when you say, suppose that x is an A, that's the first time you're specifying x, and so you're choosing some arbitrary x within A. And so this sentence can be omitted, and we simply can say, suppose x is an A, and it is understood that we're choosing some arbitrary element of A. And so now we have our lemma. So now we can come back to the proposition. And because we have this lemma, this question is now answered. Because now, of course, notation, we switch the letters around. A here is actually what was B in here. Whereas U what was A and C is B. But the lemma still applies. And so what we have is, since A is a subset of B and U is a subset of A, then U is a subset of B. And now we get the proof of the proposition. So now let us prove the proposition. So as we mentioned, we want to prove if A is a subset of B, then the power set of A is a subset of the power set of B. And so we're choosing some arbitrary element within the power set, which we call U. And so we can go ahead. And so I'm going to write now different style than Bellman. So I'm just going to say let U be in the power set of A. And as with Bellman, this is saying that now U is arbitrary. It's arbitrarily chosen in the power set of A. So by definition, U is a subset of A. By assumption, we have that A is a subset of B, and so it follows by lemma 1 that U is a subset of B. And now we use the definition of what it means to be a subset. And so in particular, so by definition, since U is a subset of B, we have that U is an element of the power set of B. But now we have started with U is in the power set of A, and we have shown that U is in the power set of B. And so since U was arbitrarily chosen, surely we conclude that the power set of A is a subset of the power set of B. And we are done. And so what I want you to do now is to take a moment and consider the following question. Is the converse true? And so recall that whenever we say the converse in a conditional statement, it means the reverse implication. So if we were to assume that if the power set of A was a subset of the power set of B, is it the case that A is a subset of B? So that is, if the power set of A was a subset of the power set of B, then is A subset of B? So pause the video and ponder this. Do a quick example, and when you unpause, we will tackle this question. And so if we were to prove this, we have our given power set of A is a subset of the power set of B, and we want to show that A is a subset of B. But we can go ahead and choose some arbitrary x's in A, and we want to show that that x's in A is an element of the power set of B. Of B, not the power set, but an element of B. And so we can go ahead and replace that in this manner, since we do want to show that if we have some element in A, then that is an element of B. And so we have this here. But now, how do we use this with the power set? Well, if we have that x is in A, that means that the set containing x is a subset of A. But if we have a subset, then we have an element of the power set of A. And so that's telling us that we have some x in the power set of A by definition. But now, if we have an element of the power set of A, that element must be in the power set of B, because we have this assumption. The power set of A is contained within the power set of B. And so we would have that x has to be an element of the power set of B. And now we just continue doing this, because we can go ahead and say if x is an element of the power set of B, then that's the same as telling us that x is a subset of B, which in turn tells us that x itself is an element of B. And we are done. We have a statement. So it turns out that the converse is true, and so we can now prove it. So now let's go ahead and formally prove this. So here we have, so suppose we have our assumption, power set of A is a subset of the power set of B, and now we're going to go ahead and choose some arbitrary element inside A. So we have our x is an A. Then the set containing x is a subset of A, and by definition we have that x is an element of the power set of A. Consequently, we have that x is in the power set of B. And so in this case, since we already stated that the power set of A is a subset of the power set of B, we can go ahead and make that deduction, since it's quite recent since we stated it. And thus, x itself is a subset of B. So in particular, x is in B, which shows that A is a subset of B. And we are done. We have now proven the statement. Now, the proof I did here and the one that I did for the previous proposition are slightly differently worded. And so something that has been brought up in our synchronous session is, must we write down the assumptions? And so here the assumption is the power set of A is a subset of the power set of B. And so in this situation, I opted to write it down. And in the previous proof, I did not. I did start by saying let U be in the power set of A, but I did not write down that A was a subset of B. However, I did mention this phrase when I used it. By assumption, A is a subset of B. And so these are two perfectly valid ways of writing a proof. When we use that assumption, we can say, by assumption, we have this, and then we state it at that moment in time. And this is something particularly useful when we have a very lengthy theorem statement or proposition statement. Now, putting everything together, what we have done with this proposition is prove one direction and its converse. So we can upgrade this proposition to a theorem. And we can simply now write theorem. We can now what we have shown is that if A and B are sets, A and B be sets, then the power set, actually let me use to keep that notation from the first statement. So then A is a subset of B if and only if the power set of A is a subset of the power set of B. And so now we have rewritten the statement so that now it's an if and only if. And if we were to prove this, well, we have already done the proof, but when we are doing a if and only if proof, we first do one direction and then the converse. And so what we could do here is write a forward arrow and then copy the proof that we just did. We can copy the proof for that statement over here, and that will go there. So here is the copied statement. So we have one direction. And now for the converse, we do the same exact thing. We go ahead and now write a backwards arrow here, and we go ahead, copy the proof we just did. And there we have it. Now we have the converse that we've showed, but now we have our proof for the same result, but now written differently. And so whenever we are proving a result that has a biconditional, so an if and only if, you want to do it in two steps. You first assume one direction, so here we assume A is a subset of B, and you show that the power set of A is a subset of the power set of B. And once you have done that, you can then do the reverse direction. So suppose that the power set of A is a subset of the power set of B, and show that A is a subset of B. So for our next proof, we are going to consider a theorem that is covered in our textbook. And so what the theorem states is that if A, B, and C are sets, and A minus B is a subset of C, then A minus C is a subset of B. Now, to prove this, we have the following assumptions. I'm going to put in our scratch work. Our givens are as follows. We are told that A minus B is a subset of C, and our goal is to prove that A minus C is a subset of B. But, as we have done before, we're trying to prove this set containment, so we want to choose an x in A minus C, and it suffices then to show that that x is also in B. And so we can go here, go to our givens, we can take our x to be in A minus C, and then our goal is then replaced by x in C. So with this, we can now go through and see what does the x being in A minus C entail. Well, by definition, this is the same as x in A, and x is not in C. Oh, I made a typo. This should be x is in B, since that's what we want to show. We want to show that x is in B. So where do we go from here? And so now we are going to do a contradiction argument. And so here's the intuition for why. We have a statement about A and C. Specifically, we have a statement about how x relates to A and C. But we need additional information to use this given about A minus B being a subset of C. And so what we are going to do is, if we want to show that x is in B, there's two possibilities. X is in B or x is not in B. So if we were to do a contradiction argument, so in other words, suppose x is not in B, and show that that leads to a contradiction, then it must be the case that x is in B. And so that's exactly how this argument will go, is that by assuming that x is not in B, now we pair that with the assumption here that we have x is in A. We have, by definition, that x is in A minus B, but by our given, A minus B is a subset of C. And so now x is in C. But x is not in C. Contradiction. And a shorthand notation for scratch work that we could use when saying that we have a contradiction is this symbol right here of a forward arrow and a backwards arrow. And so this is a common use in scratch work when we're going through an argument. We can go ahead and simply say this here to denote that we have our contradiction. And so therefore, x must be in B. and that finishes the proof, since that's what we wanted to show. But now, in terms of precision, in terms of the logical framework for the proof, this is a contradiction argument. But it's not the same as the ones we considered last time, where we had a statement of the form P, which is what we have, implies Q. Because we did not negate Q, but rather we were using contradiction to get that X must be in B by assuming otherwise. And so when we formally write this, we don't write that this is a proof by contradiction, since we are not negating the consequent in this situation. And so here's the proof. So let's go ahead and take our X in A minus C. So by definition, X is in A, and X is not in C. Now, we're going to claim that X is in B, which is our goal. So we claim that X is in B, and so here's where we use that contradiction aspect. And so suppose otherwise, so that X is not in B, then X is in A and X is not in B, which by definition yields that X is in the set difference of A minus B. But now we use the assumption. And so since we have not listed that out, so by assumption, A minus B is a subset of C, and thus X is in C. But we have established that X is not in C, and so we have a contradiction. So therefore, X is in B. And so that's what we have used that contradiction aspect, is that by assuming that X was not in B and getting a contradiction, now we have X in B, and we return back to the proof, because now we have that our X is in A minus C, and we have now shown that X is in B, and so consequently A minus C is a subset of B, which concludes the proof, and we're done. And so we are done with the proof for this. The next statement we're going to do is also from the text, so it's the following theorem. So we have two families of sets, F and G, and we are given that the intersection of F and G is non-empty. And we want to show that then the intersection of the families of sets F is inside the union of the sets in G. So how do we go about this? So if we do our scratch work here, so we have F intersect G, so our givens. So we are told that F intersect G is non-empty, and our goal is to show that the intersection of the families of sets in F is a subset of the union of the families in G. And so what we are going to do is show that if we take some x in here, then that x has to be inside here. So we want to go ahead, so we can go ahead and rewrite that as some x in the intersection of the families of sets in F, and then show that that x is in the union of the sets in G. So what can we do with these givens? So first off, what does it mean for the family of the intersection of the families F and G to be non-empty? So this means that they have to share a set in common. And so there is some set A that is in F intersect G. Since now we're looking at these are families of sets, and so we must have that there is some set A that lives inside F and G in the set of the families. So we have this. So that's using this here. Now what does it mean to be an x in the intersection of the families? Well, that means by definition that we have that the intersection of the f's is the set of all x's such that for every single set A in the family, it is the case that x is an A. But now, if we put that together, we have that A is an F. And by definition, we then get that x has to be in the set A, because this is a statement about every single set A in the family of F. And this is one such set. So that x has to be in here by that definition. And so we have that this x has to be in A. But now, A is also in G. And so if A is in G, and we have that x is in A, which is in turn in G, then we have that there is at least one set A in the union of the family of the sets in the family of G by definition. And so that's the intuition of how we go about this for the proof. And so now we can go ahead and write this formally. So proof. So suppose that F intersect G is non-empty and X is in the intersection of F. So the next thing we're going to do, just move this up here, is use the fact that this here is non-empty. Since F intersect G is non-empty, there is a set A such that A, it lives in the intersection of the families. So thus, A is in F and A is in G. Since X is in the intersection of the families, we have by definition that X is in every set in the family F. And so in particular we have that X is in A. And so we can just write what I said verbally over here, that X is in each set of F. In F. And thus, X is in our set A, since A is in F. In particular, x is in the union of the g's, since A is in G and X is in A. And so now we are done, because we have established that this X is in the union of the G's, and we chose it to be in the intersection of the F's. So therefore, the intersection of the F's is a subset of the union of the G's. And so we're done. And so this is an example of an existence proof, where we had an existence argument, because we were told that the intersection of f and g was non-empty. And so that told us that we could find a set that lived in the two families of f and g. And so we chose that set. What is that set? Well, first off, f and g are some arbitrary families. But by having that premise that this is non-empty, we know that there is at least one set A in their intersection. And that's the set we chose. And then we proceeded. Another type of proof that we could do, where we have a statement about existence, is the following question, which is exercise 25 from 3.3. And in this case, we are being tasked with proving that for every real number x, there is a real number y, such that for every real number z, yc is equal to x plus z, quantity squared, minus x squared plus y squared. And so now, the key thing for this one is that we have for all x, there exists a y, such that for all z, and then we have the given statement here. But what we want to do for this proof is we want to find, so I want to find a y that depends on x, which makes this equality hold. Since by the way that this is phrased, in terms of the quantifiers, we have that y depends on x. So for every single real number x, we can find such a y. And so we want to be able to write y as y equals some quantity in such a way that we do have this equality. So before we begin, and whenever we have this is where scratch work is important, what happens if we try to solve for y? What do we get? Well, to do so, let's expand the right-hand side. So we expand the right-hand side, we have x plus z squared minus x squared plus z squared. But then the x plus z quantity squared, that becomes x squared plus 2xz plus z squared minus x squared minus z squared. And so this simplifies to just 2xz. And we want this to be equal to y times z. And so that's the equality that we want to have. And so this equality holds if y is equal to 2 times x. And so here's the thing about proofs like these, is that when we write them formally, it's done backwards. Because we went about expanding over here to get that y is equal to 2x. But now for the proof, when we write this formally, we're going to start in reverse. So let y be equal to 2 times x. Then we end up getting that yz is equal to 2xz, which in turn is equal to x plus z quantity squared minus x squared plus z squared. And then we can go about expanding in the same manner and show that this here is, these are equal, or leave it as this, and we are done. We're done with the proof. Because now the z does not depend on y, only the x does. Sorry, I said that backwards. Y depends only on x, and so z here is arbitrary. And so now we have established that for every real number x, there is some real number y, such that for every real number z, we do have this equality here. And so we are done. We have proven this statement. And so for our next lesson, we are going to continue. We're going to do section 3.5 and come back to induction, and we're going to see another instance of a existence proof using induction. So specifically, we're going to be proving what is known as the division theorem.